Hi everybody, welcome to new video. Sorry about the gap, I was travelling and I got these while I was away. Quick note before we get started, what do you think of the new camera angle? Let me know in the comments if you prefer this to the old one, you prefer the old one over this one, what should I do? These here, easy use branded 10 LED melon shaped light things. I got them in Mr. Price in Ireland for €2-ish, which is about £1.50 or about $2 depending whatever currency you use. These things here, they have a timer built into them, on off, IP44 rated, which is interesting to me. I was intrigued to see how they'd done that, because usually with these things, the IP rating is pretty terrible. They just don't have anything at all. As soon as they get even slightly damp, water gets in, they're destroyed. So we'll have a look at those. Information on the side. You can read to that, I hope, if you'd like. There's nothing all that interest on them, fairly standard. 6 hours on, 18 hours off on the timer, powered by 2 AA batteries. But this is the impressive bit. The box on these, have a look at the back, CE marked, category 3, which is, it basically means they're not mains powered, IP44 rated, everything else in the back not really relevant. But properly sealed here, proper clips on the side, proper rubber gasket the whole way around, and a proper mating surface over here. These will actually keep water out. I haven't tested them yet. I'm going to probably test it when I reuse this box for another project, and if it fails I'll let you know. I'll probably put a description, note in the description if it fails. These lights though, they're reasonably attractive. They were on clearance, I should have said. They were on clearance because it is no longer summer. It is actually snowing outside as I'm recording this, so people are not interested in melon-shaped lights. One thing we will do before I take them apart is I'll show you them running as they are at the moment, using my bench power supply because I don't have any AA batteries on hand. Black lead to the negative, red one to the positive. The power supply is set to 3 volts. We turn them on, you can see the melon lights up. Yeah, what do you expect? The melon lights up when you turn them on. They're lights. But they're drawing about 40 milliamps, so 10 LEDs in parallel, 40 milliamps, that's 4 milliamps per LED. They're not actually baking these, which is again surprising. Usually they overdrive the LEDs to the nth degree and they die very, very quickly. These actually will probably last a fairly long time, so if you're looking for a brand, these first impressions seem pretty good. I'm going to take this box off and use it for something else because I really quite like this box actually. I'm wishing I bought more, but I couldn't bring more back due to luggage space constraints. Thanks Ryanair. I also found one of these when I was walking back from the bus station. So I'm going to take the cell out of this. We will use the cell from that to power these, which is another useful thing you can do with any set of LED lights like these. You can do it with 3 volt ones, 5 volt ones. You can make them USB powered with just like a USB lead if you wanted to, using the same method. Very useful. I'll show you how to do that. So give me one moment while I get my stuff and we'll do a little bit of maths to work out what size resistors we need and stuff. I'll show you how to do all that. One moment. I know there's maths on the page, don't worry, this is very simple, I'll go over everything for you. Basically, you need to do a calculation like this if you're going to try to power a set of LED lights off of something else that's not the battery they've come with, just to make sure we don't damage them. This is Ohm's law. If you already know what Ohm's law is, you can skip over this. My explanation is going to be boring to you. If you don't know what Ohm's law is, I'll try and explain everything so that anyone who wants to can do this. Would be a good soldering practice project or something. This over here is Ohm's law, V equals IR. You can remember the 3 formulas, or as I prefer to do, you can just remember this little diagram here. The way it works is you cover the thing that you want to know and it will tell you what the voltage or what the formula is. So if I cover the I symbol, it tells me V over R. As you can see over here, I equals V over R. Yeah, that's how I prefer to do it. You can do it however you like. What we're going to do is we're going to take the formula here for us, which is resistance, so R equals V over I, and we're going to use that to calculate the size resistor we need. I'm using a lithium polymer battery, which has a nominal voltage of 3.7 volt and a maximum charge voltage of 4.2 volt. So for me, V equals 4.2 volt. If you're going to use a USB power supply, which you absolutely can do, you just take a phone charger cable, cut the end off it and strip the inside. There'll be 4 wires if you use a USB-A one. I wouldn't recommend using USB-C because that gets complicated. You need additional resistors and stuff. So stick with USB-A, which is the rectangular one like that with the thing at the bottom. Inside there will be 4 wires, a red wire, a black wire, a green wire and a white one, usually. You can cut off the white wire and the green wire, they're data wires, you don't need them. And the red and the black wire are the only ones we need. The red wire is positive and the black one is negative, usually, but it's very important, check that with a multimeter first, because sometimes they're wired backwards because, again, China, what do you expect? If you're doing that, voltage equals 5 volts. Unfortunately though, we can't use this voltage because what we have is the LED and in series with it is the resistor. The LED will be dropping a certain amount of voltage across it, and the resistor will also be dropping voltage. If we use 5 volt, then the current will be wrong, because that will tell us how much current will flow if we're dropping the whole 5 volts across this resistor, and we're not, because some voltage is being dropped here, and some voltage is being dropped here. These are white LEDs, so they're going to draw about 3-ish volts is the norm. I measured these ones, they only drop 2.5 volt. So what we have to do is take 4.2 minus 2.5. That will equal 1.6 volt, which is the voltage that will be getting dropped across this part here. So we're dropping 1.6 volt here and we're dropping 2.5 volt up here. With your set, it will be slightly different. What you can do is just take the colour that the LEDs are, so warm white for these ones or whatever the colour yours are, and Google volt drop, insert colour LED, it will tell you, use that. Again, if they're higher voltage than just these ones that run off 2 AA batteries, it gets complicated because sometimes they're wired in series, not parallel, but with these AA ones here, just Google LED, insert the colour, volt drop, and it'll tell you. So we have 1.6 volt, that's the voltage we need, and the current, I, equals 0.03 amp. This uses amps, not milliamps. I'm again dropping it slightly just to keep them tamed down. So, R equals V over I, R equals, I'm getting out of shot, R equals 1.6 over 0.03. So R is equal to, this is where you need your calculator, 1 second. Awkward jump cut while I grabbed the calculator that I definitely didn't forget to get. 1.6 divided by 0.03 equals 53.333, so 53 ohms. Now, we have to then work out what value of resistor we're actually going to use, because you don't get every value. 56 ohms is a standard, but I don't have it. What I do have is 22 and 33. 22 plus 33 is 55, which is pretty close. The standard values you'll get are 10, 22, 33, 47, 56, 68, and 100. Again, don't ask me why they're weird like this, it's a long story I'm not going to get into. But basically pick whichever combination of these will get you as close as I can. With resistors, when you put them in series, they will, when you put the resistors in series, they will add up. So I'm going to have the LEDs are like this with the power. I'm going to put one resistor here and one resistor here on each power rail. 122 ohm, 133 ohm, yes, 133 ohm, and that will give me, when you add them together, 22 plus 33 equals 55 ohms, which is pretty close to that. That's what I'm going to do. So now on to the actual work. In case anyone's interested, this is what's inside. I'm going to take a closer up picture for you, which I'll put on the screen now so you can have a look at it. It's a chip, ASIC chip, application specific integrated circuit. There's not anything to say about it, so I'm going to keep this short. This step here, very important. All I've done, I've cut the battery box off, I just stripped the ends of the wires back. But LEDs do care about the polarity, which means that the plus and minus have to be the right way around. All you have to do to check this, you just have to take the ends of the wires, put your multimeter onto diode check setting, and then put the one lead on black on one lead and the red lead on the other one. If it says, see there, 2.5, and the LEDs are glowing, I don't know if you can see that because of the lighting on the desk, but that tells me this polarity is correct. If I put it on the other way around, the meter will say OL, which means it's the wrong way around basically. So do that, work out which is which. Very important you do that. If you get it the wrong way around, the LEDs just won't work and you probably will destroy them. They'll never work. Another important thing is I am going to use the battery out of one of these devices which I picked up off the street. This has what's called a lithium polymer battery in it. Lithium batteries are angry. If you don't treat them properly, they will explode, quite literally. They'll shoot flames out, they're bad. So you get these modules here like this one, which are special, they're called protection boards. It has a USB port on here, and these output terminals here. The way it works is it takes the 5 volt power from the USB supply and regulates it to make it safe to charge the battery with. These have a default charge current of 1 amp, which is ideal for these. The smaller devices that you get, like this one here, another one I picked up, I have yet to take the cell out of these yet, but those ones have smaller cells in them, so ideally they'd have a lower charge current. If you know what you're doing, and you already would know about charge currents if you know how to do this, but there's a resistor on here that sets what the charge current is, so if you can change that, amazing. If you can't, don't really worry about it. It just might reduce the number of cycles you get out the cell before it loses capacity. Anyway, these modules, very, very, very important. If you don't have one of these modules, bad things will happen. You can get these very cheaply on eBay, Amazon, AliExpress, any of those kind of places. Just look up TP4056 charge module. That is the name of the main IC on this, is a TP4056. There's millions of sellers selling them, very cheap, just get some. The other important thing to point out is you'll get some of them which don't have this bit on the end, they just have this big chip here. Those only provide charge protection. These other 2 chips on the end here and the 4 pads here, out plus and out minus, as well as B plus and B minus, those mean that this provides discharge protection as well as charge protection. So they will cut the load, they'll turn the load off if the voltage on the battery gets dangerously low, because with lithium batteries, if you discharge them too low and then try to recharge them, they can explode. So yeah, get some of these. Getting the cells out of these is very easy. All you have to do is just take the bottom cap off and pull the cell out. These ones here will require a flat blade screwdriver. This is the problem with having a messy bench. I can never find... One second. There we go, screwdriver. So, as I was saying, the way you get the cells out of these, very easy. You just take the screwdriver, you see there's a slot on the back of, or on the side of this. You just put the screwdriver in the slot, careful not to hurt yourself, and usually you can push the tab in and pop the end cap off like that. The end cap will pull off, and you have this bit here, which is the pressure sensor to detect when the person inhales through the device. You pull this out, you'll get this bit in the end here, sometimes comes out in the tube. That's full of nasty, horrible liquid that stinks. Don't touch that. Just pull this bit out, like this. Sorry, I'm out of frame again. Pull this bit out, pull this out. This here is the lithium battery that we are interested in, and this bit here is the heating element, which again is nasty and I don't want to touch. All I'm going to do then is just get some wire cutters and chop through the cables. This is the bit we're interested in. All of this can just go in the bin, which I will throw over there. Same, these bits here just go in the bin. One way that you can tell if these are still good or not is if you blow on the chip here, they will flash the light, and if the light comes on, it means the cell's still good. So I assume you can see that. When I blow on the thing like that, the light comes on, that means that this cell is still A, working, and B, the voltage is not fallen low enough. These don't have any protection in them because the cells are supposed to be single use, and as I was saying, if the voltage has fallen too low, it's not safe to recharge them. If the light on this still comes on, it means the voltage is high enough that you can use it still. So what we're going to do is we're going to desolder the wires off the end of the cell. The very important thing, if you're going to cut the wires off on this, is do not cut all the wires at once. If you do that, you'll short the cell out and you'll get huge current flow. If you're going to cut these wires, cut them one at a time. Or just desolder them like this. So take the soldering iron and heat the blob on the end. Take the wires off. Actually I think most of the little package things in these devices, which, like these can things, some of them have chargers built into them, but using them is difficult and not really worthwhile because they don't have the undercharge protection. So I would recommend just buying one of these boards. I do have a datasheet for one of those modules somewhere, but I'd have to see if I could dig it out. Actually finding one of those was a nightmare. There. So, if we have a look on this, hopefully this cell has markings on it. I don't actually see them. That's annoying. 1 second, I'm going to take this tab off. I think they're probably underneath that. So, here is a picture of the markings as I suspected they were under the thing in question. And here are a couple of pictures of the more readable markings on some other cells. The one I took there, as you can see, has 5.1 watt hours on it, rather than an amp hour capacity. Watt hours are just another way of saying it. The other cell you saw there had amp hours and watt hours on it. You can convert between them, I won't go into how. Either way, that gives you the information about what size your cell is. It is important to say, going back to video, that some of the devices have cells like these. They look like capacitors, they are not capacitors. These are lithium cells, and band indicates positive, not band indicates negative like you get on normal electrical capacitors. Important to remember that. They usually have a circuit board soldered on the end here. If you find these, if you know how to use them, great. If you're new to electronics, probably give these ones a miss. Just stick them in a box and leave them for later. Tape over the contact ends so they're safe, but just leave them for later when you get better at soldering. Anyway, with this one, what I'm going to do is we will attach some wires to the ends of here. We will then solder the wires onto here, and we will then solder the resistors onto here onto the ends of the wire string. Give me 1 second because I was just realising I have lost my Kapton tape and I need to find it for this, so 1 second. So here is everything we're going to need. This is very easy. We have a couple bits of wire. You could even use the wire off the module thing if you wanted. I don't recommend that because it's so thin, but you could. I have this. This is a switch. It's a weird switch, but it's the first one I had that was appropriate and came to hand. And it will do what I want because I want this to be pretty much on all the time. So in order to turn this switch off, you have to take this little plug out to turn it off. As I said, it's a weird switch. It's designed for detecting when you have a thing that slides in and out. You put a little pin on the end like that, which pushes into the hole and turns it on and off. That's what it's for. I think this came out of a CD player or something to detect when the tray slides in and out, but I'm going to use it for this. We have the two resistors. The size and colour differences are because one is metal film and one is carbon film, which is a distinction, doesn't matter. And the other one is 0.6 ohm, one is 0.5 ohm, which is why the size is different. We have, as I said, the cell and the charge controller, and we have the lights. What we're going to do, I've already trimmed down the leads on these resistors. Usually they have two leads the same length, but I've trimmed it down. So what I'm going to do is I'm going to solder one of them to the terminal called out plus, and one I'm going to solder to the terminal called out minus. I need to move back into the frame. Can I zoom down more? No, I can't. I might zoom down in post. But what I'm going to do is I'm going to put the soldering iron on, I'm going to flow some solder onto the pad. I will do the same thing on the other pin. What I'll then do is line up the wire on the resistor to the pad and heat. Then hold it for a second, and it's now attached. I will then do the same thing on the other pad. I just put a bit too much solder on, so it wipes them off. I will put the resistor leg on and then heat. Hold it for a second, and again that's attached too. These resistors are going to go in line with the output. So I'm going to put one of the resistors, I'm going to bend round like this, and then curve the lead on it around like this, so that I can mount this switch on the bottom of the board here. What I'm going to do is solder. I will just trim this wire down like that, and these contacts already have solder on them. I'll just wipe them off a bit because again they have rather a lot. What I'll do is I'll just line them up, heat the joint, and then again those are attached together. I will wire, that's switching the negative, which is fine. It doesn't really matter. It doesn't matter which leg you put the switch in. Normally you switch to positive, but you don't have to. I will then put the black wire onto the B minus terminal. And the red wire is going to go onto the B plus terminal. We'll then solder the battery itself to the wires on this lead here. The battery will have polarity markings on it. The red shows the positive end. So I will take the battery and we'll flow a little bit of fresh solder onto the tab of the battery. These batteries only have one point of the tab which it will take solder. So if you snap the tab off the battery's basically destroyed. You're never going to be able to solder back to the end of it again. you'd need to spot weld a new copper section on, which is not something that most people would have the equipment to do. So we put a blob of solder on each end. I might tin the wires for this as well, which is where I just take the iron and melt a little bit of solder on the end of the wires. Like that. I stripped off a little bit more than I have to, so we'll crop them down. I will then take red end of the battery, red wire. We will solder them together. And black end of the battery to the black wire. Again, we solder them together like that. This is now basically done. I'm going to get this and we will wire it on. I'm looking at the markings on the wire. So this wire is the negative, which I will solder to the central contact of the switch. I'll just snip the excess off. One thing I am going to do is a quick sanity check, just to make sure that I've definitely got this the right way around. I will get my multimeter, we'll stick the black on there and the red on here, and yeah, I get a reading. Perfect. All that's left to do then is just take the other one of these wires and solder it to the output of this resistor. So I'll fold it back like this, I think. We'll crop it off there. Then I'll trim this end down a bit. Put a bit of solder onto each of these, and then flow it together. And because the switch is the wrong way around, you can see the lights are on. If I take the thing out the switch, the lights go off. Perfect. That's pretty much it. That's all you need to do. One of the other things I'm going to do, just for safety's sake, 'cause this is a bit of a mess, I'm going to take some of this, put the lights back on. This is called Kapton tape. It's basically just electrical insulation tape, but special. It's designed for electronics uses rather than electrical ones. I'm going to take some of this, I will wrap the wire, I will wrap the contacts, I'll cover everything up and make it all nice and pretty and small. I will be back in a second after I've done that, because it's going to take a while of fiddling and I can't do that on camera because I have to do it closer to me. So yeah, I'll be back in a second. So here we go. I taped round the cell with Kapton tape, which is the correct tape to use for this kind of thing. Then I've wrapped it in black insulating tape to make it a bit prettier looking, so that it's easier to hide when you're putting the lights up. You could do this with like a set of Christmas lights or something for one of the little 2 or 3 foot tall trees, so you can hide this really easily in the pot at the bottom. Makes it almost invisible when it's black. I also swapped the switch here for one that latches rather than the one that I had put in the thing. Just because I thought that was better. I found one when I was hunting around for something else. This box here, the other fruit of this project, I have an idea of what I'm going to do with this, which may or may not be a video. I'll see, it depends how the project goes. So that will go to my pile of parts. These I will probably put up somewhere. I did do a quick calculation. These, from a full charge of this battery, this set of 10 lights should run for about 2 days, just less than. I think it was like 1.9 something days that they'll run. In reality, it will be different to that because the voltage comes down, the current goes down as well, so it probably will run for about 2 days, but they'll be dimmer. But anyway, yeah. Quick guide how to do this kind of thing. If you go for it, let me know how it goes in the comments below. And you can use basically this exact same process, just with a USB lead. Cut the plug off one end, strip it back, take the red and the black, cut the other wires off from the red and the black, solder the red and the black to the plus and the minus, check the polarity first with a multimeter because it's often wrong. Use the formula I showed, just use 5 volts instead of the 4.2 volts which I use for this, and it should work exactly the same. You plug them in and they'll run. Just a quick note as well, on some USB power banks, the smart ones, you will find that they won't run properly because the power bank requires a certain amount of load put onto it, otherwise it will go in standby mode to save power from the parasitic draw from the boost circuitry, which is another thing I'm not going to explain. But if you find that you plug them in, they'll run for a while and then turn off, it'll be that the power bank you have is not seeing enough draw to make them run properly. So the fixes for that are very easy. You can either get a new power bank, that's the simpler one, plug them into like a wall charger, because they don't go to sleep. Or the other option is you can add an additional resistor in parallel to the supply, which is where you'll solder it between the plus and the minus to draw additional current. But you would need to experiment with that yourself to work out what size to use. I don't know what size would be best, because I've never actually done it. All my power banks I've never had issues with. But yes, hopefully you enjoyed the video, hopefully you found it informative. If you did, thumbs up, like, subscribe, that kind of thing, and I will see you in the next one.